And now for a deeper dive into different types of generalization, because we've talked about a lot of types of RL, which is basically kind of like one way you can think about it is zero-shot generalization. If you've got the agent and it can learn, then it should eventually figure out how to maximize reward, which to be honest is a really good bar to set for the community. Like for a while, just being able to get zero shot or like infinite shot generalization for using an RL algorithm on some new task and it learns properly and finds a good policy is still something the community is interested in doing better for. But here we're going to cover some of the stuff that's basically in between zero shot generalization and all the stuff that is sort of this version of infinite shot generalization. So here, a bit about generalization, some stuff related to robotics, but then a lot in multitask learning, meta learning. And one of the topics that we haven't covered enough in this class, we kind of like glossed over it kind of quickly when talking about like Octo and OpenVLA, which is supposed to be generalization across morphology. But this area is actually much bigger than just like visions and end effector, vision input and end effector control. Okay, so let's start with why we like generalization. In two ways to think of this, depending on which part of the community you come from. One is the idea is just to generally do more with less. So agents, basically the idea is to have some sort of agent that can work through, collect some experience, but make really good use of that experience. The same reason why, everyone can hopefully learn inside of this classroom as opposed to any other classroom in this building. Your learning should hopefully not be dependent on the wall color in the room, but we might all know that's not totally true. But for the most part, like these types of generalizations or kind of like being able to ignore some of this information and still reuse that data is kind of like, ingrained well into the system. Machine learning models are not fantastic at even some of the easier forms of generalization, like ignoring the wall color or the background for some of these generalist robotics policies is still a work in progress. So we're going to kind of formulate this much better today. And a lot of this motivation comes from, if we're talking about making humanoid robots, that eventually they can generalize well enough on physical tasks that can maybe accomplish most things that people can do. Because, like for babies, like even at the lovely young age of 6 months to like 12 months, they can already grasp a great number of objects really well. They don't really need to pay much attention to how much they're designed. Part of that has to do with the way the hand is also pretty pliable and grasps stuff well. But if we're still talking about tool use, so actually like monkeys are actually pretty good at using tools as well. They can generalize to like using sticks to doing different things in order to be able to get food better. So they can already do good types of generalization. One that I also enjoy quite a bit is being able to cook different recipes. So if you were to if you've cooked potatoes before, if you go to someone else's house and cook potatoes, still works. If you use a different pot, still cooks potatoes. If it's a different time of the day, still potatoes. And this is something that generalizes pretty well for a lot of cooking avenues, things like that. And then if anyone in the room still remembers how to clean, also being able to clean in different locations, things like that are also different forms of generalization. Some of these are like using tools and planning. Some of these are like perceptual, and some of these are grasping forms of generalization. Still, and I started a conversation with a bunch of colleagues, there isn't really a great description for the levels of autonomy for a human robot yet. Give us 2 months to work that out. But this is sort of like there should be levels of describing these different levels of autonomy and to eventually get a good generalized system. And this is where good agents should be able to either think about generalization in two ways. One is that the idea is to discover the actual causal mechanisms that exist in the world, such that these are the factors and anything else that happens in the state space doesn't bother them. Or another way to think about generalization is a form of compression. So like if there was a model that you were making to predict a function, it should be the simplest form of that function, and that kind of forces that function to ignore any just kind of like useless or unuseful information for solving the task. Sorry. Do those two make sense? Have people heard of causality before? A little bit? Okay, you probably also know making causal models is really, really hard. Yeah, so it's a fantastic concept, and maybe we'll make some more progress on that. But basically, the idea of compression is like everything we do in this class. Like training a machine learning model is figuring out how to like compress the knowledge from a data set into a bunch of model weights such that it can learn. It's a form of compression. If it's done really well and well regularized, it can usually generalize better. And that's part of like Occam's razor and part of the reason for using regularization for models. And that's where this is all helpful, because the thing that kind of messes with the ability of stuff to generalize well are a couple of things. One of them is often overfitting, which uh, it's possible the robotics community is doing a fair bit of this right now. But it's this process where if you're training your model is way too parameter heavy, then it can end up overfitting individual data points inside of the data set instead of learning, like this is Glenn's water bottle right here on the desk. And no matter where it is, if it's over here, it can still be manipulated and moved around. Doesn't matter its location. Okay. So the real question in some amounts here is to understand how much like the community is overfitting, how much this is really an issue for the robotics community. It still is a very much of an issue. I think, I mean, some of you are getting into your projects right now, and we'll probably mess around with some stuff on Wednesday during the demos. But it becomes pretty apparent really quickly that we can call and say that the models aren't working very well. They're not following goals really well. They're most likely overfitting some undesirable behavior in the data set, where it'll only work if the background color behind the robot is white, because that's what happens in a lot of the robotics data sets. Many of them look like very clean kitchens inside of those robotics data sets, which may not be entirely representative of the average kitchen in the world. It's certainly not where you'd start, because we probably want the robot to clean the kitchen, not to, you don't bring the robot over to the clean kitchen and ask it to start cleaning, something like that. Okay, so this overfitting can happen in a lot of different locations. One is it can be biased, like to overfit certain state distributions. Uh, this is part of the reason, like we talked about this example in sim to real. So when a model or some policy is trained in a simulation, if there isn't at least some noise added to the simulator in order to force that model to learn how to be robust to variation, then it ends up overfitting that simulator quite a bit, and then it won't transfer very well to the real world. So this is one of the more common cases, at least for sim to real, and that's why different types of domain randomization are done. Often there are issues with robot models that are going to overfit the dynamics. For example, I only saw this in one or two papers, and maybe it's because they were using more human-like hands in those papers. But from there, they put on like rubber gloves over top of the robot hand to show that the model would still be able to learn in those cases. So being able to adapt to those dynamics. And what is really common in RL is actually having models that'll overfit reward functions. There's a bit of a entanglement between reward functions and the distribution of states the policy visits. But it's, very often you can think of the example, okay, like maybe I want to become a professional poker player and I spend all of my time studying how to do poker. And then for some reason I wake up the next day and decide I want to be, now an expert humanoid robot designer. It may take a lot of experience and time to transfer the stuff that was learned from playing poker over to being able to make a humanoid robot. So this overfitting process is a little complicated when it comes to RL, because in this case, it ends up being two things related to a task misspecification, but also overfitting is usually this process of having a model that has too many parameters, and then it usually overfits the data. In this case, it's a version of this. The model ends up being overfit and trained too long on a task, sometimes whether or not it has too many parameters. But here there's like this reward function. The idea is that it's overfit on that specific reward function design as well. So it'll have a hard time going to another task because it's overfit on a particular state distribution so far. Does that make sense? The difference between these two types of overfitting? You'll certainly hear and read a lot of in papers, which we probably many of them in the class, where they'll say like it's overfitting a task. But remember, like overfitting is usually with respect to a model class and a data set. So just keep in mind when tasks are described, adding a little bit of like a layer of under confusion really between understanding like the overfitting model training process and what is just maybe a really simple reward function or something like that, which is more vague than talking about model classes and data distributions. Okay. General goal is still to be able to avoid wasting experience. And the idea is to even, be able to use some experience, even if some things are changed. Like being in this class, I can still carry this water bottle, whether or not it's half full or completely full. Things like that work really well. Okay. Everyone pretty clear on generalization so far and sort of like a lot of the common problems for robotics where this tends to creep in. Okay. So now let's get into some algorithms. So this is often formulated as a multitask learning problem. It's hard to be able to generalize to some other distribution unless there's at least some other distributions around to be able to train the model over. And then you can kind of leave out a distribution and then be able to see if the model actually fits well for that distribution. And then hopefully, because it's trained on this collection of other distributions, it'll be able to train well on some new task. And this is also true even for reinforcement learning or for like the large supervised learning cases that we do, that we've talked about in this class. So this is, what are some examples? Maybe if we wanted to make, let's work through this one. Let's make a conceptual, awesome sports playing robot. Okay, so what are some of the tasks this robot should learn before being able to play a sport? So you want me to give you the held out evaluation set first? I won't give that to you. Let's say it's some random sport. Okay, so I'm going to call this is just like task feet, task hands. Maybe those should be a little bit bigger. Okay. Do you think balance would be closer to this state distribution here for feet or for hands? Closer to feet? Okay. So somewhere in here, there'll be a little sub-blob for balance. All right. What else should this model be trained on? Yeah. Okay. All right. So we can edit this one. Some overlap balance with hands, give or take. Now, what else? What else do you think we need to learn to do some average sports? Is that it? It's just a lot of standing around and avoiding being pushed over? Mm. Mm. Do you think that's going to be a separate blob here, or was that going to be overlapping with these other definitions for tasks? Yeah, it's hard to do this in 3D. Hmm. All right, well, this is the prior slide. Let's pretend there's a box there, and now this is what's often called 2.5D, actually in the geometry community. So now we'll have team. We'll call it collaboration. Okay. All right. So then what else? And this is sort of like now we've kind of got two levels, so you can still put stuff in this for either option. Ideas? How about maybe think a bit more specific at a sport now? Because we've kind of been a bit general, like these all seem good, just to see if we're missing anything in a particular sport. Yeah. Can you? Okay, but does that go in at least this collaboration level, or does that go into the kind of physical control level of describing tasks? Okay. So this is uh maybe overlaps. I'll call this I'm kind of call it goal planning for now. Okay. What else? Okay. So then where does that cover in the other slide? Okay. Balance hands and feet. So there's sort of another chunk in here for get up. Okay. hmm Actually, well, it's actually a really true thing, and I spent a little while thinking about that too. Like almost everything that gets up uses its hands and arms. Just think about it the next time you have this question. Try to get up off the ground and don't use your arms at all. Yeah, so that's an interesting, even related to the fully autonomous stuff we talked about. If you have a humanoid robot with no arms and it falls down, it can't recover at all. So having it have arms is actually maybe some way to get around reset free problems. Yeah. Hmm. Okay. Have you ever played rugby before? Okay, a lot of the process is like that, where if like one of your teammates trips, half of your teammate falls on top of them and crushes them actually. So, all right, for this one, so I'm going to draw an X. This X is kind of like a wormhole that goes back up to this top level. That'll kind of maybe come out up here, something like that. And this is also part of the get up functionality of the overall world. So it's tricky to be able to come up with this. And now we're hoping, like, do we think we've covered enough of the kind of physical maneuvering space for the robot as well as some of the planning space for it to, okay, now I'm just going to pick a really hard sport. Okay. As an example, okay, the eval set um, is water polo. How well is this robot going to do? Let's say the robot doesn't get executed in water. Uh-huh. Waterproof, that's an engineering problem, things like that. Okay. But it's not, we got pretty far. Maybe if there was also in this set, we've got water polo, uh, something that was maybe more in distribution since I'm trying not to be quite so adversarial. No, but you do need to keep yourself afloat the whole time. So there's maybe balance is a bit related to that. Uh, but yeah, we can just put like football in here is probably more in the area what people were thinking about. So it's likely that for this multitask learning process, hopefully the agent will have learned some of those general skills, at least from the goal planning. There was actually a lot of goal planning. So in many ways, this top level chunk here might transfer better across both of these tasks. But this physical dynamics chunk that we discussed is not gonna probably not gonna transfer as well. There's no swimming, not much of balance. Although actually learning how to use your feet is actually pretty important in water polo because it's much easier to use your legs to keep yourself afloat. So you're kicking a lot. It doesn't burn through as much energy. Oh, yeah. So that's actually a fantastic point. So if part of this data set is to learn to throw the ball, how is that going to plan out for our evaluation set that is now water polo and football? No, I was thinking like European football, so soccer here, so not American football. Yeah. Great. Also a good definition for also to increase confusion and the challenges of specifying multitasks. But basically, is there experience that if you collect it for like throwing the ball versus kicking the ball, is there actually shared experience that'll help for both of these tasks? No? Okay. That's part of the challenge too. Like even when covering this data, now it becomes weird because some of this stuff literally, we'll talk about it for a bit, but there's a form of interference, like understanding the rules of soccer, like European football, non-American football, and then water polo are actually going to give the agent two completely different understandings of what to do at a certain point. So figuring out this whole landscape of collecting training data, not knowing exactly what the evaluation set beforehand is having some implication. And then what we're going to talk about in the rest of this lecture is at least like, okay, if someone gave, the data set to the agent that is all this data, what are some of the methods we could use to try to train it just like mathematically now to be able to hit some of these generalization hopes? Maybe at least they'll become good at one of these sports for water polo or football. Probably football so far in this case, although we never talked about kicking a soccer ball. So this is maybe a goalie, possibly, maybe not. Okay, good. But a lot of the concept here is, so this is related to transfer learning and the hope at the end, where basically the idea is there's some distribution. There is a whole lot of data out there. Even in this cases, we kind of got into this 2.5D small mess of trying to figure out even a differentiation between certain types of states. But if there is some type of transfer learning or generalization, it often means that there is some type of like lower dimensional manifold where a lot of this model exists. So more often when we think about this in terms of perception, so sure, there's a whole bunch of versions of this room. Many of them could maybe ignore the versions of the wall color, or it could still change, but you'd still physically operate in the room the same. So normally, like this y ends up being, or sorry, here the original distribution is x, but we want to find a z, such that in that representation space, the behaviors end up being the same. There's a lot of stuff that basically learns to ignore in X that are unrelated or basically just extraneous information related to solving the task. And this is where, okay, what we want for these agents is eventually learn some pretty good transformation of this form. Go from this collected data down to like the raw reusable information or raw reusable representation that has good like invariances to noise, at least in like the traditional way we think about generalization versus like invariances or like reuse across of like some other tasks, distributions, soccer games, sports, things like that. Okay. All right. So then when we get more into the robotics case, this is, all right, we've got some more robots. These days we've got some more humanoid robots, but this is the PR2 robot. Maybe it can walk your dog. Maybe it shouldn't walk your dog because it'd be good to get outside more. Folding laundry has been a weirdly popular task for decades to get robots to do, as well as cleaning. So there's some collection of tasks. A lot of these tasks are going to use a lot of the same motions, like even arm motions. If it's doing like laundry folding or cleaning, there might be a lot of like whipping around hand motions. And it's to basically learn some Z representation to go from the task, what's being designed, to what will be offered elsewhere in order to be able to map different problems to that space, or basically different states to the same representation. So from here, what we're going to talk about now is different forms to be able to learn this representation. So if there's some overlap between these states, kind of like what we talked about from before, hopefully training on overlap really in this Z space, being able to train on one of these ends up improving the basically performance on these other tasks. Because if you find that good Z representation, then things become really reusable, pretty robust and generalizable. Okay, whoops. We're not going to skip all the slides. Sorry to say that. Okay. Let's take a break there for now. Looks like we're already at 2:20. We'll start up again at 2:32. Oh. Yeah. Large concept model. Mm. Mhm. Is it encoding the whole sentence as one token? One state. Interesting. It could be useful for like goal specification because the part it might not be as good for like low level control for generalization to try and encode an entire maybe trajectory into one token because even a lot of the concept related to this problem is really we kind of want to make a hash function that takes in a lot of states, uh, what I'll call a lot of observations and leads to an actual state that it can generalize over. So designing like this hash function that's going to go from some input to say like, if you're in this room, any location in this room still corresponds to being in this room. So there's like a many one to relationship. So in this case, yeah, doing a good design for that tokenization and adjusting it is important to being able to have those options and have them generalize. So like a lot of generalization is just like finding a good hash function, which means you need for like tokenizations, you can correspond to that, like the number of bins in the hash function. And then if you have a lot of bins, then it's really hard to generalize. But if you have too few bins, then a lot of things alias each other. So like you do the same thing, even though if it's not the desired outcome at the moment. So it's a balance between this. So I'd be curious to see in that case, like how many tokens do they have to make now to describe every possible sentence? Seems like not a lot of tokens are going to be revisited. Hmm. Yeah. Mhm. I'd be curious how it's also related to VQVAEs that are like learning some code book of possible states or sentences that can exist in the data set and how those are connected. Yeah, if you want to post that paper on the like discussions channel for the class. Hmm. Yeah. The one way to get around this, and it's basically what the rest of the lecture is going to be on, is to add some basically some contextual information. So like maybe there's a way, one way to help differentiate between these two distributions is to maybe add a little bit more information to the input, such that, well, okay, well now with this information, kind of like the robots that ask for help, now it can actually differentiate between these modes that currently exist, and it's not sure which one is the best yet. Yeah, but yeah, share that paper. Pretty tricky. Discord. All right, sure. Okay, but now take a break for a bit. Start again in a few minutes. Mhm. So they're still reading in a bunch of tokens into another embedding space, and they're trying to then embed that into a shared. Hmm. Yeah, so now I remember. Hmm. I mean, that could definitely be useful for, yeah, like the goal specifications we've been talking about, because we've known the language-based models for robotics are pretty sensitive to the goal text in the description. Even if you swap in objects or add in an extra character or a space, they'll probably break. So, yeah. Oui, oui. Yeah, I see. Mm. Yeah, there's been a long history of that too, where like adding bottlenecks sound nice. Often they kind of get ignored, and then you don't learn a good representation. Okay, but yeah, like using this for learning some semantic information would be great. So that's why it's good for goals. Because we're still not great at that. A lot of models and papers these days are trying to like robotics as a control thing we've talked about many times is like in many ways been solved. Like humanoid robots have been able to do stuff for a while, but figuring out how to specify goals in a large, diverse space for them to do things hasn't worked out so well. Maybe NLP is starting to be useful there, but still tricky. Mhm. Uh, hmm. Yeah, because like another version of this, like clip is a version of this, like trying to like if a picture is worth 1,000 words, even in some sort of randomized order, it's still like similar concepts that should be semantically described and hopefully modeled in a nice way. A clip maybe it doesn't cover things as well as this one concept model. So, yeah, I'll have a look over it in that space for the future. All right. Well, let's get started again, although it almost feels like we didn't take a break. Maybe. Uh, maybe that's a good sign. It's good to see everyone still has energy on Friday. All right. So actually, strongly related to that concept we were just discussing. Um, but basically, there's a lot of different models that do different types of what I'm going to group all together today in conditional generalization. So this is just the problem of given some information. We kind of talked briefly here where like it's just an X, but I want to unpack this X here because X can be anything. And we've talked about a few examples of this in the class already, where this is basically versions of the same problem. So this is basically given some recent information, be able to infer some type of a task. So I'll start with it's a good, even though it's an older example, but it definitely comes from robotics more, is to be able to do a type of system identification. So this was a method that is still used really every day. And to be honest, the same process of what we talked about for figuring out how to like infer a goal is another form of like system identification. You need to infer what the goal is. But this was used more traditionally in the case for like given some data set that was collected on the robot for at least like a couple of minutes, then use this to train some model that can infer the parameters for that system. In this case, these parameters are more often things like PD gains, basically some of the parameters for a linear model. And then after doing that system identification, the robot could be like controlled with some good predictability, because without that, you kind of like get a robot in the mail, you've got to unpack it, put it on your desk or something like that. It might have been jostled around during that process in the mail, so it needs to calibrate itself. And to calibrate itself to figure out its frictions for its actual motors, um, things like that. Maybe it's got a little bit of weight on it or the extra hand that exists on the arm. It has to do calibration, or what is basically system identification. Run an algorithm to infer what will be the slightly new versions of these Z parameters. Okay, so that one's maybe the older version of this right for now. Another version of this is basically sim to real training, which we talked about a couple of lectures from before. This is similar to this, but you can include a little bit more information in it. This was over X's, so it was like true states were known at that point. It was just parameters to determine the physics weren't known. In this case, for sim to real, the agent now gets instead a sequence of observations, something that's kind of like what it's seen for the last, few steps. And in this case, the Z parameters the model's trying to learn is like, what is the friction at the robot? Whether or not it's stubbed its toe at this particular half second, something like that. Whether or not the masses are changing, whether or not the motors are starting to actually overheat, because then the physics and dynamics will change a fair bit. So in this case, it's still figuring out some type of model, but we're going to kind of keep changing the information that's contained inside of this. But the idea is like feed in some information, some contextual information. So it's not zero shot. It's not only zero shot generalization in order for it to be able to infer more. That makes sense so far for sim to real? Okay. Then basically a slightly newer version of this is, well, we haven't talked at all yet about in this class anyway, is you can also do this for meta reinforcement learning or just meta learning, which is this process of basically you want an agent to learn to learn. But what that means in this case is it needs to learn how to take some recent information, so some observations and some rewards that it received, and then use that information to basically, in some way in combination with parameters, output some Z that helps like some policy conditioned on that Z. It's very often like A given S, comma Z. And I guess just like phi or something like that for the parameters. But this Z is what helps it learn much faster as long as it learns a good representation in this space. So now meta reinforcement learning has just changed the type of inputs that go into this more. So we can just keep dumping more and more information into this. The more and more information and types that we dump into this conditional usually means we need more and more data in order to be able to train a good model or a good representation. So like one piece is going to need, or one concept is going to need a whole lot of different pieces of data from text, everything to model to. And then there's the last version of this, which is gaining popularity these days, which is basically in context learning. So this is kind of a generalization. If you go to the bottom, the next one is sort of like a specialized version of the previous one on this list. But kind of the strength of in context learning is now it may be possible to almost like specify the entire problem just in the context. So in here, before this was observations and rewards. Now these will be like, you can think of it as input images and like labels cat or dog. And then from this process at the end, give the model an entire data set and whys that should be labeled. And then out produces from this is basically like a whole policy where it's almost like actions, given states, and Z are almost like the parameters for the entire problem. So now you can, if we have all the data in the universe, you can kind of train the bottom problem on the data sets from all of the different computer vision problems, and then give it a short data set for a new computer vision problem. And then it'll be able to answer more or less, at least with some good accuracy, how to do well on that new problem. Does that make sense so far? Still pretty clear? Has everyone already done in-context learning before? No? Okay. So any questions? We'll get into the details for a few of these, so will probably help Park pique some interest in there too to get to these aspects. Okay. Uh, so the general process when we're doing this for control in RL is really what we talked about for a bit for putting a whole bunch of sports together, or at least like the tasks and state space for learning over sports and skills. But so that process in some ways is occasionally like it's constructed. Sometimes it looks a bit artificial. But if we're looking at the algorithm that we normally do, like in this class, what's basically added is now at the beginning of every episode, at least for like an example here, some task is chosen. Like the agent needs to collect some data for a task. A task is either a variation on a new like t+1, some new forward dynamics function, t comma a, t, or it's going to be something for a new reward function, s so t comma a. It's sort of like what changes in that task when we're talking about RL. And then from this, the agent acts, basically collects data inside of that environment, given this slightly adjusted definition under this new description for some task, and then just collects data, keeps doing its normal updates from before. So some system out there basically needs to now partition the world some way into additional tasks so it can learn these representations across different distributions. Okay, and this is where I already gave some examples for sim to real as one where, this could be, mass of link 3 is now, 2.3 and not 2.1, like how it was from before, because it might actually change a little bit after it's been delivered. And, there's always some engineering tolerances that need to be adjusted for. Okay, so there's still a lot of uh, like weird struggles in making algorithms that work really well in this space. So I'll kind of introduce a couple of these, and we'll talk about a couple of different pieces of work that kind of address each of these a bit separately. So one is, in many ways, it's been really challenging to make like large, good multitask learning methods. If the goal is to be able to increase the training and generalization, for at least a year or two, actually, this looked like this was going to not work because it would require a lot more data in order to be able to train things. It also required having better optimizers because now that when we were talking about the example of, okay, if we collected data for being able to throw like a spherical ball, but the evaluation set was water polo instead of playing like soccer. Okay, well, there's actually interference between the tasks that exist in the data set. So in that case, when like the model computes a gradient, it doesn't really know what to do. And sometimes those just kind of like wipe out parts of good knowledge in the model, and it can't figure out how to sort out that contradiction. So there was some optimization challenges to overcome. Yes, and this is related to, if you want to know more about like the mathematics of gradient interference, you should go check out a couple of these pieces of work. But basically it's that, like if you took like the one tuple from the holding the ball, or the simpler example is if we just wanted to train some like robot to walk to the left and walk to the right, and then we try and use both of those as tasks to optimize the model over. Very often the model would kind of, through pretty much randomness, either pick going to the right or going to the left and not learn the other task at all. So at least it'd be okay at one of them. But this interference would basically result in it being more challenging to be able to develop a model in that space. Yeah, one of the other common caveats is if there's a large group of tasks to be able to be performed, the model will very often pick the easiest tasks. So if inside of the data set, and if all tasks are mathematically defined as equal in terms of like loss that exists in the actual training process, if one task is to walk and the other task is to figure out how to move to Mars, it is going to very well, with far higher probability, it's just going to learn how to walk and ignore the whole task for learning how to get to Mars, when really we probably want it to help us with the problem of moving to Mars, which is far more interesting than just being able to walk. Okay. Does that make sense so far? This is also kind of like, why do we create education systems the way that we do? Like in kindergarten, we don't start with the problem of how to move to Mars. At least I didn't. I don't know if that's where you all started. Maybe in like Quebec, you've got a much more fortified and good education system than at least in Colorado, where I was doing most of my grade school. But I sort of have those balances, and then you build on these over time. Okay. And there's often kind of like some general optimization challenges. So, I mean, this is asking the policy to learn more. Before, there might have been a large space to which exists a set of parameters that can learn how to walk. Any of these will work. But now, even if we just wanted like the go left or go right version of walk, that might split this in half. It's not maybe a fantastic example right now, but this is like the theta right and theta left. So there becomes now smaller spaces of parameters that exist that can actually do well across all of these tasks. And the more and more tasks that are added, we're kind of like demanding the optimization to find an even more like smaller and refined area of the parameter space. That's kind of, I don't know, I'll call this like theta of infinity in terms of like it can work over all the tasks that exist. So this is going to take some work in order to be able to get to. That's why there's a lot of papers that look more engineering like as well, and other ones that are doing more careful like optimization methods, is to eventually find this like really hard thing to find in the optimization space. So that also makes this more challenging to optimize. Also because these days, these parameters are growing in size, so it takes even more compute. And then this kind of ends up being stuck in an area around the no free lunch theorem. How many people are familiar with the no free lunch theorem? A little bit? Okay. All right, good. So it's kind of this idea where it's kind of like no perfect model that's good at everything. The original version is sort of like no algorithm that can possibly be the best at all possible tasks. Because if you have got a little bit more structure, you can always make a more efficient version. So at least a lot of what came out of the meta learning community is it's definitely a version of this no free lunch theorem, like making one model that's going to be, you can't have one model that is sort of like always the fastest, the quickest, fewest amount of like memory that's actually used in order to be able to compute a solution across all tasks, unfortunately. But that doesn't, we shouldn't not try because we can actually get kind of close. And a little bit of these algorithms is they are trying to bend this rule a little bit because now there's a lot of context in these models for how all these are described. So because there can be a lot of information that's kind of given to the model, it offloads the model from having to like store all the information for all those tasks in the parameters. At least just needs to figure out where to look in the data in order to be able to find a good solution to make learning faster. Does that make sense? Now maybe we're having like a cheaper lunch, even though it's not a free lunch now. Okay. Okay, went a little too far. Great. So despite all of this, we should definitely still keep going down this paradigm, and we'll find some trade-offs here and there, but it doesn't mean we can't make some progress. Okay, so then one of the first challenges that was basically dealt with here is figuring out how to deal with this. If the model is presented with some distribution of tasks, it'll focus on learning the easy ones, and it actually will kind of avoid learning the hard ones because they might come at the cost of learning the easy ones. So this would happen a lot in options framework, a lot of stuff in hierarchical RL, even that we've talked about already, like these goal conditions policies, S of A given S comma the goal, and then some theta. Models will often do good at the easy goals, like stuff that's not very far from the state, and it'll fixate on those for a while. It'll be hard to expand that space of goals. So, okay. So there's kind of two ways to get around this. So one is basically train over all the tasks separately. So if the first problem of just being able to eventually make a giant multitask system, kind of, this is like step one, there needs to be solutions for those tasks. It's sort of like if you want to go and learn how to do like play a bunch of different sports, you probably study all those individually for a little while. And then maybe later in the evening, a process comes up where you need to think about how to integrate all that knowledge together. So this is basically like develop, a policy that is call it pi soccer on its own. And then another policy it's going to call pi, we were talking about water polo. So then in this water polo case, so now you have at least policies that are good at both of these things. And we'll definitely still run into a few problems, but now it's basically try to integrate both of these. So not the learning process of collecting data and solving it, but basically the outputs from these, do supervised learning on those just to try to put them into a single model. So it makes this process easier such that now there's going to be some other policy pi soccer slash water polo. So basically kind of offloading the integration process to later in the pipeline. It's kind of hard to like be able to learn a task and collect new data from it and integrate it into everything else that you do. I don't know, you probably haven't done this yet in your education system, but it'd be, maybe you remember high school a little bit more where you'd go through like 6 different subjects in a single day, and that might not give you a lot of time to focus on any one individually. So it might actually be harder to integrate all those. But maybe if you did like 3 weeks French, 3 weeks English, 3 weeks math, something like that, and then at the end thought more about how to integrate those together, it might make it at least easier to kind of split this process apart. Okay. Does that make sense? So then the weird part is that there's still many ways to go about this. And because we're still trying to be as efficient as possible. There's maybe some middle ground between like totally collecting data on new tasks and then just doing all the training at the end. And you can have these different paradigms here. So this multitask one is like the one that doesn't really work too well. This is every task at the same time. This parallel one is treat all tasks totally parallel. Let's pretend you've got W copies of the agent in order to be able to train and then figure out how to distill those together. That's basically this example. And then there's one that uses transfer learning to at least do a little bit of efficiency. So kind of like learn one task first and then transfer that task to that policy to the new task and then learn that new task second. So that at least these arrows here denote transfer such that at least less data should be needed on those other tasks that it's learning. And then still at the end, distill things together. So in this process, this really is, the idea is this version on the right, it's more data efficient because it can at least transfer some knowledge from other tasks. The version on the left here is parallel, doesn't get to use any transfer information from other tasks during the learning process, like the data collection, figuring out how to solve the planning problem task. Okay. So not necessarily. So this first task could be the easiest or the hardest task possible, but at least it gets to focus on learning just that task. And then that actually would be an advantage over here for kind of like part C. At least if an assumption here is that this hardest task covers a lot of the state space well, such that it would help a lot for transferring to the other tasks. So then it would mean on all these new tasks, it's not going to have to learn a lot because it's transferring a lot from its previous policy. It won't have to collect a lot of new data, for example. Having the distillation process at the end always seems to still be like really helpful in terms of, because this policy, when transferred to a new task, it gets to transfer some information. It's going to forget about some of the stuff from this previous task now that it's in a new task. It's kind of like, yeah, if you go from like French, English, math, maybe when you get down to math, French is getting a little bit rusty. I need to do some more French later that week to get back to it. So sometimes there's a cycle that kind of goes back in here, at least in natural life. Yeah, does that make sense? Yeah, there's still a lot of like challenging concepts in here, but that's the overall idea for like maybe splitting tasks apart in order to be able to like kind of like conquer one at a time. Or if you got the option, do some transfer between tasks while conquering all of them and solving all of them to be more data efficient. Okay. All right. So also, again, I made way too many slides for this particular lecture. So if you want to get even into more details for a couple of algorithms in particular for this, you can go and check out this work for Plaid. I think I'll skip over this one for now though, because the next one also kind of covers this area. Okay, so it's basically like that link goes to a whole nother set of slides. If you're interested, dig into those. You can even leave comments on them that I'll get to later today or for the next class. Okay, so this hasn't used any meta learning from what we've talked about from before. This is basically just the challenges of being able to train a model when there's many tasks. So then a better, or at least a more good way in order to be able to formulate this problem, because here we have these blue arrows, which are just kind of like doing magic. I said that they would transfer information from one task to the next task. That is basically, there's a large question mark over how well that transfer happens. So if you learn on one of the hard tasks in the first hand, how certain can the agent or algorithm be such that transfer will actually happen on the next task? So meta learning here is actually going to think more carefully about structuring this problem such that if you train a policy in this space, it's like at least mathematically guaranteed to like give some improvement on the next task that it could be seen. It like shouldn't be any worse, and at least better than starting from some total random policy or some model without any information. And it's this idea of learning to learn. Basically, this general process of when an agent would be able to visit new data, part of what it's ingrained into its own parameters or its design is being able to more efficiently capture like mutual information between the new data that's coming in, how it relates to previous tasks that it has seen during its training process, and then being able to update its parameters faster in order to be able to get closer to a more optimal solution that'll be able to basically get, in our cases, higher reward. So this is used in a lot of different areas. One of these, like you can use it for model-based RL, such that, you know, if you've got a robot that's walking along, and it happens kind of often where like maybe one of the motors wears out, if it's doing model-based learning at that point, it might be able to pick up really quick that one of its motors has started to wear out and then adapt like its planning module and update the parameters that describe that friction such that it can quickly adapt via this process. There's also just generally doing policy gradients, where it's to, if the reward function changes, or even the dynamics in some way, in that case, it can just collect like a trajectory or two in the new task that it's learning over now in order to be able to quickly be able to update towards that task. All right, so this is basically, so far we've talked about this generalizing to unseen tasks. Like the entire class up until now has mostly been train a big giant model and what we call zero-shot generalization, where there's just no extra information, just here's a state, better do perfect on that new state or new task. So then this is these versions of here where I was talking about like policies with actions that have some states and some context, which called Z. We're really trying to figure out, well, now you're given some information on the task and you want to do the best, the agent wants to do the best possible given like the least amount of information. Again, a really hard problem to ask for the agent to figure out how to do that learning process, but it is a good formalism and a good path to go down in order to make better algorithms. All right, so let's go over this example. So figuring out how to get an agent to learn. So one, it needs to be able to learn again. It's a kind of its own version of going from X to Z. So this good representation such that that like representation in Z has a lot of mutual information with the task space. So it captures a lot about what's going on and will be helpful to differentiate between tasks and provide good information. So here is an example. You consider this just in general. All right, learning a new board game. So, all right, how many people have played board games before? Fun, almost everybody. Okay, fantastic. But a lot of the times you probably played some board games, and then once you start to play more board games and you're trying to like start a new board game with a friend or anyone, but the problem is maybe you want to figure out how to explain the rules of the board game. So in this case, if you've played some before, like if you played Monopoly, and then maybe you're going to play some other game that's like Monopoly, you might very often specify the rules. It's like Monopoly, but the money is a different color, and there's also this monkey that throws random bananas at you or something like that. But you're using the information from describing, I don't think I actually have a copy of Monopoly, but like using that process to actually be able to like, you're kind of like helping because both people or some people have played the same games together, borrowing a lot of the rules to like help specify how the game is played. And that's a lot of the process we'll talk about here. This was mine last year. So there's a few more that have been added on to this now. Yeah, but also I play a lot of Board Game Arena online, which also has a ton of games and is pretty cheap as well. That was the savior of mental health during COVID, was basically Board Game Arena. Anyway, yeah. I mean, I'm a researcher. I like being given hard puzzles and also collaborating with people and figuring it out. So that's how this goes. But this is sort of like a nice example that I think it seems like, at least by hands raised, most people have tried from before. So then let's operationalize this process of figuring out how to basically learn what are like the average cases for all the rules that describe board games, like mathematically, and then be able to like transfer that information real quick. in order to help someone, or at least an agent, perform well, on the next or newest board game they're trying to play. Okay, so in this case, we've got a set of parameters for the model that we're going to learn. There's some loss function that is going to be used to basically describe like doing better on that game, or basically that overall learning process. So this ends up being the loss for the actual task. So this is the loss is the difference between this function f that's going to output, f basically outputs uh, y hat, basically the prediction outcome at the moment. And then the loss here is going to be like the difference in the output from this model with respect to the actual labels for the true y. So this is describing supervised learning. So there shouldn't be anything too surprising here yet. So if we know that on some distribution of like inputs for like x's and y's, this is the loss function, then we can kind of use this as a concept. Well, the idea would be, well, actually, on some new task that the agent will train, the hope is that when given a few x's and a few y's for that new task, that new problem, it will only require a few examples from that data set and a few gradient steps in order to be able to end up with a very small loss here after those steps for being able to learn. And then in that case, if that's the goal, which is like get some data, get a low loss, then one option to be able to do well and perform well in this is now to add this as its own optimization inside of another optimization. Yeah, so like I said, this is the supervised learning setting, and then to enable this fast adaptation, basically this meta training process will be over these parameters to train some task to efficiently adapt to some new task. And then basically it results in this objective. Okay, so let's just say the notation here is very similar. There's some D that describes a data set of X's and Y's that describe inputs and outputs for a model. Here there's some objective function. It's kind of the same version of what we've talked about back here. And the idea is to have this objective function now be lower after some gradient updates. So then here what is developed is instead, here's the loss function we talked about in the last slide, which is the gradient to adjust the overall parameters of this model such that they're good on this training set, which is full of a number of training sets, so a bunch of different groups of X's and Y's, and then some test set that after updates are performed on this one test set with its own X's and Y's, then it gets good loss on that test set. But really what it's doing is figuring out over here what are going to be the parameters such that once the parameters to basically start from after learning across a bunch of what should be similar tasks, so there's some shared information, such that when an update is done from these parameters, the loss will end up being pretty low on this test set. So basically some set is held out from this. That's like a whole supervised learning problem. And then there's a bunch of other training sets in here that describe various problems. And then basically train a model in this case such that it'll end up getting good performance quickly across all the training sets, and then most importantly, that test set that comes after the training process. It's a very weird process with a kind of long gradient chain where it's compute a loss here and then compute a loss on the outer side of this. And you basically want to figure out, okay, if you could come in and change the resulting parameters for the inner process to make the outer process easier, do that. And then iterate over that process many, many times. Okay, does that make sense so far? Yeah, this is very much the kind of figure out how to do the rule process for games over time, like figure out to almost have like your short description of all the possible rules for board games. And then if someone, or you start to play a new board game and they give you bits of information about the game, you can very quickly update from that rule book to figure out, okay, these are the rules to play this one that'll be best applied from what's been learned before. Okay, so that's the overall framework. There is definitely a lot of optimization challenges in this. You've already went through a couple of homework assignments. You've already seen some of the challenges in just training like a normal RL agent or a normal supervised agent. So this is now an optimization on top of an optimization. So the number of hyperparameters to get this working and the balance and doing good optimization kind of gets an order of magnitude worse. And that's kind of a short story for the field. Whenever you want like a more flexible algorithm, something that learns to learn, it's going to come at the cost of being harder to design, usually being trickier to figure out, requiring more data and more time to do hyperparameter tuning whenever you want something more from an algorithm. Okay. Any questions so far? Meta learning? Okay. Great. So there's a couple of different ways to still encode meta learning, because this is the definition from MAML specifically, which is like trying to find a set of initial policy parameters such that a gradient step from those parameters results in good performance. Technically, this can be done in a lot of different ways. One is actually to train an RNN such that like when it feeds in data, it'll output a set of parameters for the whole policy that'll be good to be able to predict over that model. So it's the main process here is to like train a model such that given a bunch of data, it produces a good set of parameters on the new task. So one way to do this is you can just treat this as a sequence problem, train an RNN over many, many data sets such that it'll eventually produce some parameters that are good on some new input data set. Very much like the in-context learning that we talked about a few slides ago. This is good, but this is very prone to overfitting when using an LSTM or an RS or an RNN. They don't scale well to large amounts of data, so they tend to not work well beyond like smaller distributions of tasks. One of these, which is the one I just introduced for doing MAML, it's got a lot of good properties. In fact, it even has good structure. If you want to go read this paper and like the universality of the problem, as in like it's almost always guaranteed to at least provide some improvement. Here, the RNN, it's kind of dependent on the loss, and it's hard to write some good mathematical theory to say that like with more data or more training, it ends up extrapolating better. It really depends on distance out of the training set. And the one that really kind of makes it hard to use this version is the number of samples needed for this particular problem can be quite vast. So if you're using MAML, there might need to be like orders of magnitude more data to get a good performant result using that algorithm. And then there's, interestingly, there's the other version of this, which is train a model that just takes in some data, outputs a Z, and then you can condition a policy on that Z. This is kind of like the sim-material training that we've been talking about. This also doesn't necessarily have good theoretical properties. So this is just kind of an inference problem. But it's not easy to say that pi of A given S and like the new Z that comes out of the model. It's really hard to describe the generalization properties of like now given a new Z, will the policy still be able to work well with that Z? Does that make sense? It's just sort of, it can be given anything here. So it's really hard to have some description of the types of properties that'll work over those distributions, such that, okay, given Z's in this distribution, it'll still perform well. It's not totally impossible, but without a lot of additional structure, like saying these models are all linear or something like that, you can't actually describe much of a correct like policy improvement theorem. You can do that technically for the model agnostic meta learning model because it's mostly talking about parameters. So like in the parameter space, not some latent space. So because the parameter space is the same as the policy space parameters, like here, these are all kind of like sharing versions of theta. It's easier to like write some good proof to say like there will be some improvement using those parameters. Okay. Thanks. Yeah, so POMDP is the partially observed MDP. So it's just, you only get observations. And even as Sometimes, at least outside of the RL literature, this is called an inverse problem, where it's given a pile of data of sampling some system, figure out the inverse problem, like what was the parameters of that original system beforehand. So it's sort of like, if you wanted to infer the shape of this water bottle, you'd probably need to record a video of the entire process. And then from that, it's possible to like reverse engineer the geometry for the water bottle. So this is very much a infer the unknown parameters in the MDP because there's only observations, not states. And states are fully observed, give all the information needed to determine the best action. Basically never happens in the real world, but is mathematically nice to use in some frameworks. And the challenge for this one is, because there's no like smooth kind of function and analysis that can be done for using Z, it does get pretty prone to overfitting. So the policy will maybe overfit certain Zs pretty heavily inside of the training set. And then when given a new Z during the like evaluation step, it's not always well guaranteed that it'll perform well there. You have to be like very careful about the sampling process and hopefully kind of cross your fingers a little bit. Okay, makes sense? All right. So I think I'll have time to cover one or two more things. So in this case, the part that some people also discuss as being one of the challenges in this, so even for like all these meta learning tasks, there needs to be some sort of construction of splitting the universe into different tasks somehow. We talked about this for a bit for like studying like hand control, and we didn't get into swimming, but balancing. But tasks don't often normally just generate themselves in the real world. Often they're kind of constructed in these cases. It's like, well, now all these tasks look similar and they can be used as such. There's a little bit of work in being able to figure out how to do meta learning processes without explicit task specifications. And that'll just make it easier so we don't have to organize data into a bunch of different buckets for different tasks. Sometimes this happens a bit naturally in the world, but it's still a bit constructed. So there's kind of two choices. One that you can look into is being able to infer the boundary. So like figuring out, are the new states that much different from the previous states that we're seeing? And if they were, change and label this as a new task. And then one piece of work that we worked on for a little bit was to be able to detect local state distributions and just kind of see if you can do it more implicitly than explicitly as the model's training. Because the agents just kind of like locally change stuff in its own distribution. That way those can be implicit in terms of tasks that change. Kind of like the weather changes every day outside. So you can just treat every day as a new task and just not worry about the details too much. People seem to be pretty good at creating artificial task boundaries in learning. Okay, so I'll cover maybe something for another minute, but I think I'm probably going to have to give a little extra time. So one of these, all right. So has anyone read the DeepMind's ADA agent paper from before? This is like a year or two old. So they did in-context learning for RL at a massive scale to see if they could basically do meta learning with a transformer rather than having to do the mammal process that doesn't scale. So they would generate a whole bunch of different environments, train across hundreds of millions of these environments, and then have a different task. So it wouldn't necessarily, each of these would be a different task, but then it would train it such that it gets to collect like a few trajectories in each of these environments to help it infer like the shape of the environment so it can find its goal location fast, or at least fast in terms of like rollouts in the environment. So you can go read this paper. It was actually published, so it was okay for me to include it in the class, so it's not too confusing. But this is basically like using transformers and in-context learning to do meta learning. So the model used a design curriculum, which we've already talked about for a bit, where it would randomly sample a bunch of those environments, pick from them a bunch of the ones that haven't been solved quite yet, so it can focus on trying to solve those rather than just the whole distribution of tasks. So it's already got that like selective task solving. The environment or the policy for the model wasn't extremely complicated. It's use a big giant transformer, use a lot of in-context learning, so it could feed in trajectories from previous experiences. So the idea is collect a lot of some trajectories on new randomly generated environments, and then the evaluation set is going to be another new environment. And it'll get to collect a few trajectories on that environment and then use it in this model that predicts a value and an action. Obviously, what ends up working better in this case is using a transformer, just because it seems to scale a little bit better for processing over larger batches of data. I also tried using an RNN that didn't work as well. There's also some computational challenges there. And then here you can also see like the importance of the like task selection process. So here, just using totally uniform selection across all possible environments doesn't result in the best performance. You need to have a good education system that builds on skills over time and then can finally offer like hard stuff at the end as what motivates the agent to learn more and also have a good curriculum to get into that hard stuff. And they also showed, so this is kind of the meta learning slide here. So this is with basically one shot. So the agent gets to collect one trajectory in that new random environment. Its performance goes up a little bit, but given an additional trajectory in that environment, and then given a few more, up to about 13 is how much experience it kind of needs to have enough information to infer like the environment and the task in order to perform well in that environment and task. Okay, does that make sense here? We kind of covered this a bit in the meta-learning part, but one of the other points for meta-learning is how much data is the agent able to collect on the new test environment. And meta-learning does not scale too well to doing more and more rollouts because then it needs to do more and more rollouts on every task to collect data. Although that's kind of the more realistic example. Yeah, and you can look at, there's actually a couple of people at Mila working on basically doing an open source reproduction of this, so you can study this process a lot more. So you can have a look at a few of those links and maybe ping them if you're interested. And that's basically most of the process for this paper. So kind of like use a big transformer, use a lot of data, have a couple of thousand spare computers that no one else is currently using, and then just kind of crunch numbers over this for a while. Okay. Any questions about the ADA agent? The idea here is like these concepts at scale can work well. The meta-learning formulations, some of them didn't scale as well in the way they could process data. The newer stuff for doing in-context learning seems to scale much better, although it still requires a fair bit of time and compute. Okay, great. All right, at this point, hopefully you can all do me a little favor. I'm going to leave a bit early, and the nice gentlemen in the back of the room are going to have a few questions for you about me and maybe general stuff about the class as well. So besides that, have a good weekend. The weather's getting pretty nice, so enjoy that. There's nothing due on Monday, so don't worry.